Do you guys have questions from the homework? From 3.1, it talked about quadratic functions and identifying polynomial functions in their graphs. So it looked like the quiz went pretty well, from what I could see. That's good. I also checked and it looked like more people were doing the homework now, which is also a good thing. The quizzes, I think, are going to end up just becoming a little bit more of like a check for understanding, and they're not going to have the same type of questions that you're going to see on an exam for the most part, just because I don't want to have to go through all the steps of having you submit your work. Okay, well, if there aren't any questions from 3.1, feel free to turn on your cameras so I can see you, see one of you. And then we'll continue forward. Thank you. Oh, we got more? Thank you. Let's continue talking about polynomial functions. We need to talk about end behavior. It's a really important concept. All right, so last time, just to remind you, oh, gotta share my screen here. All right. Last time we were talking about what is a polynomial function. I gave you this big definition here, and we basically stated that the major things were that your polynomial function cannot have radicals. You can't have any sort of rational exponent. You can't have variables in the denominator. So we went through a couple of examples of what types of functions were polynomials and which ones weren't. Then we talked about the graph of a polynomial function. And we said that polynomial functions of degree 2 or higher have graphs that are smooth and continuous. And don't forget, the reason we specify degree 2 or higher is because technically a first degree polynomial is a linear equation. So it's just a straight line. A second degree polynomial gives you that quadratic. By smooth, it means the graph contains only rounded curves, no sharp corners. Continuous means you can graph it and never pick up your pencil. Now, the end behavior is what's occurring to the far left and the far right of the function. So basically, if we took x all the way to positive infinity or all the way to negative infinity, what would happen to the y values? And that's what we're going to focus on next. So we have 4 possibilities here. Here we go. And they all involve the degree of the polynomial and the lead coefficient of the polynomial. So when you're seeing at the top, case 1, if n is odd, n means the degree of your polynomial. So you're looking at the exponent on the first term of your polynomial, assuming that your polynomial is written in descending order. That means the powers go down as you move from one term to the next. If n is odd, then you have 2 possibilities. Now, n being odd would mean you have some polynomial that's like x to the 3rd, x to the 5th, x to the 7th. You're really not going to see anything higher than that unless it's just for purposes of talking about what the end behavior is, but you're certainly not going to be graphing like x to the 9th power polynomials. That would be nuts. Okay, if n is odd, if the lead coefficient is positive, then the graph falls to the left and rises to the right. Now, I tend to always think about this as really the graph is, in essence, going up from left to right. So as long as you have n being odd, so some sort of odd degree polynomial, if your lead coefficient's positive, which means that number that's being multiplied by that variable is positive, then your function is really just going to mostly be increasing from left to right. You're going to have weird stuff in the middle. You don't know what happens. That's why it's represented by dotted, like a dotted curve. It could be anything in the middle. You don't know. What we do know is the end behavior. We know that as the graph continues to head left for values of x, it's going to go down for values of y. And as the graph continues to head towards even more positive values of x towards infinity, your values of y are going to increase. Now, that's going to be the opposite for if n is odd and your lead coefficient's negative. I always think about this as the graph essentially going down from left to right. You'll have a bunch of crazy stuff in the middle, but the end behavior will show that you're going essentially down from left to right. So as x gets very, very small, y gets very large. As x gets very, very large, meaning heading to the right, y is going to get really small, so heading downward. But either way, one of the most important things to note here is that if n is odd and you have some odd degree polynomial, then you're always going to have something opposite happening on the left and the right. So it's either going to be one side goes up and the other side goes down, or vice versa. Now that changes when n is even. So that would be, for instance, a quadratic polynomial. So we talked about those quadratic functions being represented by parabolas. Notice that, you have a second degree polynomial, you have this parabola, and either both ends are going down or both ends are going up. Same idea here for any sort of even degree polynomial. You'll know which it's doing is dependent on the lead coefficient. So if the lead coefficient's positive, then your graph is going to rise on both ends. If your lead coefficient's negative, then it's going to fall on both ends. And again, if you need to remember this, think back to what happens to your quadratics. You know that if you have ax squared plus bx plus c, if a is positive, the graph opens up. Same idea here. It's just we're now generalizing this for polynomials of larger degree. So those are the 4 things that we need to remember here. We're going to use it all the time. They're in your notes, so you have them. But we're going to be using that throughout 3.2. So what we're going to do now for number 3 is determine whether each graph shown is the graph of a polynomial function. Why or why not? And if it is a polynomial, describe its end behavior. Before I do that, does anyone have a question about end behavior, about what we just looked at here with these graphs and these different cases? Okay. Wonderful. Number 3. So number 3 is a graph that looks like an absolute value graph. It's in the shape of a V. What do we think? Does this look like a polynomial function? No, look, I can actually see somebody like shaking their head. No, this is amazing. Thanks, Evan. Yeah, Evan says no, and he's correct. It's because it has this sharp point on it, we would say that it does not appear to be the graph of a polynomial function. Remember, and this was discussed on the first page, your polynomial function is going to have a graph with smooth rounded corners. This is a sharp point. It is not a smooth rounded corner. So you would say sharp point on the graph means that it would be not a polynomial. Oh, sorry. Okay, so it does not have only smooth rounded curves. Therefore, it is not the graph of a polynomial function. It's very likely an absolute value function, which is not a polynomial. What about this one? What do you think? Polynomial, not a polynomial? Oh, I see Beth says no. Anybody else? Oh, Sebastian says no. Now this time Evan is like nodding yes. Are you saying yes to this one, Evan? Is it because of the smooth rounded corners or the smooth rounded curves? Yeah.
Because of the rounded corners.
Because it's rounded, right? But that is kind of tricky because in the last example, that was what kept the graph from being the graph of a polynomial. In this case, yes, we do have rounded corners. However, the graph is not continuous. For it to be a polynomial function, we must be able to draw the entire graph without ever having to lift our pencil. And in this case, I could draw part of the graph, and then I can't draw the other part without lifting my pencil. So for this one, we would say, no, the graph is not continuous. If you take calc, you will talk all about continuous functions all the time. It'll come up like every single day of your calc experience. You'll get so tired of writing the word continuous. Okay, what about this one? What do we think? Polynomial or not a polynomial? Polynomial, what do we think? Yes, people were nodding when I said polynomial, and then I quickly said not a polynomial. How many of you think not a polynomial? I have no takers. Okay. I feel like I'm just teaching to like 5 people right now. Yes, polynomial, very good. You guys were right. The few, the proud, the 5. Yes, this is a polynomial function. Yes, because we would say that it is a continuous graph with rounded, smooth curves. You can say that about it. If you want to abbreviate continuous with C-O-N-T, be my guest. It's continuous with smooth curves. Now, if it's a polynomial, we have to talk about its end behavior. So the way that we're going to describe the end behavior will be the same way that it was given to us in this diagram. So we're just going to use the words, for instance, rises and falls, depending on what's happening on each side. So for this one, you're looking at what happens as the x values go to the left. And sometimes this is hard to think about because all you're seeing is that the graph is going up. But really, the x values are indeed still heading to the left. They're just starting to get there much more slowly. As your x values go left, your y values go up. So that means that our graph rises left. And we would say it falls right. So, and again, your x values are moving to the right. It just looks like the whole graph is heading down. It is, but the x values are still getting larger. What about this one? Polynomial? Not a polynomial? I got 2 takers on polynomial. Polynomial? Okay. All right. We got a new recruit for polynomial. Awesome. Yes, this is a polynomial. It is continuous with smooth curves. So now we can talk about the end behavior. Now, just as we saw in the previous graph, as the x values head to the left, the y values go up. So we would say that this end behavior rises left. But now this must be an even degreed polynomial. We don't know what the function is, but it must be even degreed because the end behavior is doing the same thing as x goes left and right. Because the graph also rises right. Any questions about end behavior? Okay, we're going to be talking a lot more about it today. We're going to be using it to do some graphing a little bit later. And by the way, prepare yourself because you're going to have a graphing by hand homework assignment to correspond to our lesson in 3.2. I already have it set up for you. I'm just going to send out an email. But if you want, actually at the end of class, I'll tell you what the problems are. But I will send an email also just so you have it in writing. Okay, so we are going to use factoring to find zeros of polynomial functions. Now, we'll talk in a minute about what zeros are, and then we'll identify zeros and their multiplicities. So if f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. Now, this is not stated within your definition, but the zeros are really just x-intercepts. Sorry. So I don't know if you have heard this wording before, zeros of a function. It just means the x-intercepts of the function, essentially. All right, so these values of x are the roots or solutions of the polynomial equation, f of x is equal to 0. We're going to be using this concept later on in the chapter to solve equations for values. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. If r is a 0 of even multiplicity, then the graph touches the x-axis and turns around at that 0. So we're going to be doing today is we're going to be finding the zeros by using factoring, and we're going to say what's happening at each 0. So to do that, we're going to look at the multiplicity. If the multiplicity is even, 2, 4, 6, 8, you're going to say that at that 0, the graph touches the x-axis and turns around. If r is a 0 of odd multiplicity, then the graph crosses the x-axis at that 0. So you've got two types of behavior that are going to be occurring from these x-intercepts that you're going to be finding, that you're going to solve by factoring. So odd multiplicity means it crosses. Even multiplicity means that it touches. If you have no idea what multiplicity is, you are not alone. I'm going to explain it when we get to this example. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. So that's an interesting fact that you may or may not remember or use, but it is helpful. Okay, so here's how we're going to do this, and I'm going to show you how the multiplicity works. Find the x-intercepts, or zeros, of the polynomial function. State whether the graph crosses or touches the x-axis at each 0. Find the y-intercept, and then use the leading coefficient test to determine the end behavior. So, so far we've only talked about end behavior given a graph. We're going to talk about it now in terms of an actual function that's been given to us. But first, we're going to work on finding the zeros for the x-intercepts. Now, I want you to be careful here. Does anyone notice something that could be problematic about this function? Open up my chat in case anybody wants to type it out. Or feel free to speak out if you notice anything.
Is it because it's cubed?
Because it's what? Cube?
Cube.
Yeah, what's the issue with the cube? Why is that problematic? That has something to do with it.
Wouldn't it become the leading coefficient? Or like the higher power?
Oh, that's fine. Okay. But Nancy, did you have something else to add to that?
Oh, I was kind of going to say kind of the same thing. Like, isn't it supposed to be in the front?
Oh, yeah. Is that what you were thinking, Evan, that the order was wrong?
Yeah.
Yeah. You're right. Yes. Whatever term has the highest exponent should come first. That has to be your leading term. In this case, you don't have that situation. It would behoove you to rewrite this in descending order. Now remember, when you switch around the order of your terms, keep the sign that's in front of the term. I know sometimes it doesn't matter in our lives whether the terms are in descending order, but in this chapter, this whole chapter, it matters a lot. Okay, so we fixed that. Now, that's not going to make a difference for us finding x-intercepts, but it will make a big difference to us when we talk about end behavior. All right, so to find the x-intercepts, we're going to use factoring. So let's go ahead and take our function, and we're going to rewrite this by factoring. So go ahead and take out the GCF. If your first term is negative, you can take out a negative. It's really not going to make a difference. It's just going to make your life a little less confusing. And you have, at most, 2 factors of x in common between your terms. For some of us, it's been a while since we factored. but it'll come right back to you. When you take out two factors of x in the first term, you're just left with one factor of x. And don't forget you factored out a negative. Positive 6 divided by negative 1 is negative 6. So you have to correct for that sign. You might be thinking, oh, big deal if I forget that. Well, it will change one of the values of your zeros, and this is your base information, so this is pretty important. And you already took out both factors of x, so right now you are done with that. All right, so we have x squared, or I'm sorry, negative x squared times x minus 6. You can always check this by distributing it back in. Negative x squared times x is negative x cubed. Negative x squared times negative 6 is positive 6x squared. Okay, now back to our definition here. We're going to find these roots by solving for f of x is equal to 0. So we're going to set this quantity equal to 0. And now we have two things occurring. We're going to use the zero factor property, which you used previously in algebra. Oh, I guess we used it when we were solving quadratic equations in 1.5. And we're going to take each factor and set it equal to 0. And then we're going to solve for x. X equals 0 and x equals 6. These are the zeros of our polynomial function. Does anyone have a question about how we found them? Okay, Sebastian asked a question in the chat. That's a different function, right? Which function, Sebastian, were you referring to? When we rewrote it? Or here? Oh, this was for the question way before. Oh, sorry. Did I neglect to answer a question that you had previously? Oh, he's fine. Okay. Just making sure. That's why I don't like to click on the chat, because then it doesn't beep at me anymore. Oh, you Googled it. Okay. Okay, well. All right, there's always Google. At each 0, state whether the graph crosses the x-axis or touches the x-axis and turns around. This is where your multiplicity comes in. If we have a multiplicity that's even, the graph is going to touch the x-axis and turn around at that 0. If our multiplicity is odd, then our graph will cross the x-axis at that 0. The multiplicity is how many times that factor popped up, that factor that you used to solve for the x-intercept. In this case, we had two factors of x, and we set that equal to 0. And then we ended up getting this 0 of x equals 0. Because of this, we would say that x equals 0 has multiplicity two. Now, when we found the 0 x equals 6, we had a factor here of x minus 6, but the factor only appeared one time. You're going to see instances where you end up with some sort of exponent on a particular factor. In this case, the exponent on x minus 6 is just 1. So our x equals 6 has a multiplicity of 1. Once you find the multiplicities, you can talk about the behavior of the graph at each 0. Does anyone have a question about the multiplicities? Okay, so once you find those multiplicities, go ahead and make your conclusion here about each 0. So we can say that x equals 0, or we can say the graph, I guess we might as well be complete, will touch the x-axis and turn around at x equals 0. Now, you don't have to write it in a complete sentence. If you just want to say, like, touch and turn, that's fine. I've even had students in the past be like, can I just use a diagram and, like, no, just say touch and turn, something like that. Something. Crosses, touch and turn. It's not that difficult. Don't say T and T, just touches and turns, that's fine. And then the graph will cross the x-axis. Well, it's not going to do anything else. There's no and. At x equals 6. Okay, so that conclusion was just based off of the multiplicity we talked about when we found those x-intercepts. The y-intercept, remember to find the y-intercept, we let x equal 0. We find the y-intercept by finding f of 0. In this case, because your function only has x terms in it, 0 minus 0 is going to be 0. So your y-intercept will just be this 0.00. But you can kind of see what we're doing now. We're leading to this point where we're going to be graphing these polynomial functions ourselves. In order to graph a polynomial function, we're going to find where it crosses the x-axis, where it crosses the y-axis, and when it does cross the x-axis, what is it going to do? And the last important piece of information that we're going to need for this is the end behavior. Now, going back to your original function, I'm going to just rewrite mine here. It's pretty short. To determine the end behavior, I'm going to use that lead coefficient test. So first of all, I need to make sure that my polynomial is in descending order. We already thought about that, and we already switched around the terms so that we had the cube term come first. Now we're going to decide if we have n odd and we have a negative lead coefficient. So our lead coefficient is less than 0. We know that if n is odd, we've either got this happening or this happening. And remember that when your lead coefficient is negative, it's going to look like your graph is going down from left to right. Sorry, I don't know if this is backwards for you when I do this. Down from left to right, I think, right? Down. I wish I could be back in a classroom right now, just like, well, then at least I would know what you could see from front and back. Okay, so you know that your end behavior is going to look something like this. Don't know what happens in the middle. It could be anything. Well, you kind of have an idea at least. If you need to draw a diagram first, I always found that helpful because I never was good at memorizing which one was rises left, falls right, blah, blah, blah. Sometimes it helps just to draw a little diagram of what's happening in this function. And then you can much more easily look at this little graph and say, okay, it must be the case that our function rises left and falls right. Now we're going to go through a couple of examples of this type where we're just going to be finding the zeros, determining the multiplicity of each zero, finding the y-intercept, and looking at the end behavior. Now, if you really wanted to get kind of an idea about what's coming ahead, and I think it's a great idea to do so, think about what we know so far. We know that we have zeros at 0 and 6. I want to plant the seeds here. We know that for our end behavior, we're going to rise left and fall to the right. We also know that at 0, the graph is going to touch the x-axis and turn around. So if it must be the case that we rise left, you don't know exactly where it is, but you can sort of signify this, and falls right. Again, we don't know exactly where it is, but it's doing something like this. If it's going to touch and turn around at 0, and cross at 6, the only way it can do that is to go through here, and then the touch and turn around has to come somewhere from above, not below. This is the basis for what this graph looks like. Now, what happens in the middle isn't super exciting. You can already connect the pieces, and you already know what's happening here because you don't have an x-intercept that lies to the left of 0. The only thing it can do once it touches and turns around is go up. That's it. And the only thing you can do to the right of 6 is fall. Now, the only thing that leaves to question is how high up does this get before it comes back down again? And to determine that, all you would need to do is just evaluate the function for a value like 3 and see what sort of point you get. Now, we're not doing an official graphing yet, but this is what we're heading to. Isn't this really cool though? You can, I mean, there was no graphing calculator involved. All we did was use the algebra that we already knew, and here's our polynomial function. We almost have the whole thing. All we need to do is just see, how high does this graph go? Not sure, but you know the point's got to be somewhere in here. Somewhere. But this is the skeleton of our function. Oh, I love this. Does anyone have a question here? I know, I get really excited. This whole chapter is great. This whole class is great, but really this chapter, so fun. So fun. Okay, let's do this again. Little bit of a different function. Notice this time we don't see any sort of issue with us having the wrong order here. Our function's already in descending order, which is great. That should be one thing that you look for right away. You should start to notice when your function's not in descending order. Okay. F of x equals x to the 4th minus 36x squared. Same directions. Let's go ahead and find the x-intercepts by taking our function and setting it equal to 0. Now, to solve, whatever you do, please don't add 36x squared to both sides and divide both sides by x squared. You're going to lose 2 of your zeros that way. If you'll remember from algebra way back when, you learned that you should have as many zeros as you have the degree of your polynomial. We have a 4th degree polynomial. We're expecting to have multiplicities that add up to 4 here. So let's go ahead and solve this by factoring. Take out x squared because x squared is all you have in common between these two terms. Now, when you factor out the x squared, that leaves you with, in the parentheses, x squared minus 36. Now, if you would like, at this point, you could use the zero factor property and take each factor and set it equal to 0. Or you can factor this one step further. I recommend doing so because sometimes students forget to take a plus or minus when they do the square root property. So I'm going to factor the difference of 2 squares here. Let's see, a squared minus b squared is a plus b times a minus b. That's the difference of 2 squares. For those of you who don't remember, you learned how to factor using that in your prereq. And this, I think, is better as far as multiplicities are concerned also, to just completely factor it before you use the zero factor property. Does anyone have a question at this point? Okay, and just in case you don't remember the difference of 2 squares, it used to be called dots. That's how we would refer to it. Difference of 2 squares. So a squared minus b squared is a plus b times a minus b. That's your factoring formula. And you'll find that you'll probably use that quite a bit in this class, but definitely in this chapter. Okay, so notice, by the way, that you're going to have another situation where you're going to get a 0 at 0 that's going to have a multiplicity too. So let's go ahead and set our zeros apart here using that zero factor property. And then we can discuss multiplicities. But the multiplicities come from this step right here. All right, take the square root of both sides and you get x equals 0. When you take, by the way, a plus or minus on both sides, when you take the square root, -0 is also 0. My son today, he's 5, and he was like, what's -0? What is that like? I'm like, you know. But he saw me making your quiz, and he was asking me all these great questions, and I was like, oh, I really want to talk to you about all of this right now, but I have to get this quiz done. And I hope that he asks me again later. He's very into negative numbers right now. Love it. Okay. Now, x equals 0 came from this factor, x squared equals 0. So here we have a multiplicity, and you can go ahead and abbreviate that, of 2. If you write mult on your exam, I will know what you're talking about. You have a factor of x plus 6 right here. There's no exponent on it other than 1. The 1 is not shown, but it's there. So your multiplicity is 1. Same for your factor of x minus 6. So your factor of x minus 6 gave you the 0, x equals 6. And the multiplicity is 1. And that leads us right into B. All of this sort of flows together. You find the zeros, you figure out their multiplicity, and from there you can talk about the graph's behavior at that 0. So we know that at x equals 0, we have a multiplicity 2, so the graph will touch and turn around at that 0. We know that at x equals -6, the graph is going to cross through that 0 because the multiplicity is odd. And at x equals +6, again, your multiplicity is odd. Your graph is going to cross through that 0. And actually, you have one kind of similar to this that you're going to be graphing on your homework. Any questions so far? So now we'll find the y-intercept. Again, when you find f of 0 for this function, all you have are x terms, so you're just going to end up getting 0. So your y-intercept is just 0, 0. So sometimes you'll glean some more interesting information about your graph based on the y-intercept, but not always. All right, as far as the end behavior is concerned, we're going to look back at our original function. The degree of the function is even, just like a quadratic function had an even degree. So we know that the behavior is going to be the same on both sides. You just need to figure out, do both sides rise or do both sides fall? Rise? Fall? What do you guys think? Rise or fall?
Rise.
Yes, you're right. Thanks, Evan. Yes, the end behavior on both ends is going to be rise because of the fact that your lead term is positive. If the lead term is positive, both sides are going to be going up. So we're going to say, and if you need a little visual, basically it's something like that. You don't know exactly what's occurring there. Rise is left, rise is right. Excellent. And if you're going for the skeleton graph, you can get a really good idea of what's happening here just by plotting your zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I think it's really good for us to practice just looking at what this stuff does. Sometimes students have a hard time putting it all together at the end. So I really kind of just like adding this little piece to it at the end just to plant the seeds. Okay, we're crossing at -6 and 6. Our end behavior rises on both ends. There's nothing else that happens between 6 and infinity that doesn't go up. It must be the case that if we cross through here at -6 and +6, we can go ahead and say that the graph is just going to continue to move upward from there. Now, the part that students sometimes have a hard time putting together is the next part. What's happening at 0? You know the graph touches and turns around. Some students like to say, okay, well, it must be the case that it does something like this, touches and turns around. Be careful. It can't do that. If that were to occur, then it must be the case that there's something connecting this piece over here to that piece over there. If there's something connecting these two pieces, there would be another 0 in here somewhere. And there would have to be another 0 in here somewhere. We don't have any other zeros. We only found 3. So this can't be. And sometimes we need to just start drawing some things with dotted lines and then getting rid of them if they don't work. The only other way to touch and turn around at 0 is to approach 0 heading upwards and then leave 0 heading downwards. And this is, again, the skeleton of your graph. The only question you'd have to ask yourself at that point is, how low does the graph go? We don't know. It is an even function. If you were to actually do the test on it, you'd find that it's even. So it will be symmetric to the y-axis. So all you'd have to do is just figure out, like, what is f of 3? And that would give you a really good indication of how far the graph goes down. Might not be the absolute farthest, but it would get you close. But since we don't know that for sure, I'm just going to fill it in with a dotted line. When we do our official graphing, we'll plug in some points and get a better estimate. I mean, who knows? It could go down really low and come back up again. It's hard to say. Probably not, but hard to say. Okay. Questions on number 5. Okay. Number 6. In some ways, this one's going to be a little bit easier just because this one's already factored for you. You are going to see some like this on your homework. You're even going to see a graphing problem that's given to you like this on your homework. In order to find the zeros in a case like this, you just need to take what was given to you, that function, and set it equal to 0, and then just use the 0 factor property to solve for those 3 x-intercepts. So we have -x cubed times x plus 3 squared times x minus 8 equals 0. A little bit less work here because we have no factoring to do ourselves. Notice that your multiplicities come straight from these exponents. The 0 that we're going to get from here will be 0. That's going to have a multiplicity of 3. This guy is going to give us x equals -3. It's going to have a multiplicity of 2. This factor will give us a 0 of 8, and it will have a multiplicity of 1. Okay, so here is where we have these multiplicities. And we have x plus 3 equals 0. If you want to include the square on it, fine. It's not really needed. I'll just include an additional step. But now you can kind of see where that multiplicity comes from. Multiplicity of 2. And then the other one is x minus 8 equals 0. X equals 8 will have a multiplicity of 1. Okay, at each zero, give its multiplicity. Fine, already did that. And state whether the graph crosses, touches, and turns around, which it does at each intercept. So at x equals 0, the multiplicity is odd. An odd multiplicity means that you're always going to be crossing through. Even multiplicity means you touch and turn around, and that was happening at x equals -3. And then x equals 8. Multiplicity is odd, crosses. So nothing too crazy here. For the y-intercept, again, you're finding f of 0. Be a little bit more careful here because even though, yes, you do have x involved in each term, well, it's not just x squared, it's x plus 3 squared. So when you substitute in 0 for x, you don't get 0. You get 0 plus 3 in this case, and 0 minus 8. So make sure you're actually evaluating f of 0. Okay, so 0, and in this case, because of the fact that we had a negative x cubed on the outside, it's going to still keep us everything is going to get multiplied by 0, so it's going to 0 it anyway. There are going to be a lot of cases where you don't have this factor of x on the outside, so you actually will have a value that's something other than 0. The box around that. Okay, questions so far? So let's talk about end behavior. This one's a little bit trickier as far as end behavior. Does anybody want to take a stab at the degree of this polynomial? What is n in this case?
Is it rises on the left and falls on the right?
Rises on the left, falls on the right. No, but I think I know where you came from up with that, and I'm really glad that you did, because I think that you're using n equals 3 and the lead coefficient being negative. Is that correct, Nancy? Yes, and I thought you were going to do that, which is why I'm specifically asking here what n is, because n is not actually 3 in this case. What is n in this case? It's not 3.
Is it 5?
It's not 5, but you're getting closer.
6.
It is 6. Chase says 6. Why did you say 6, Chase?
Because it's 3 plus the 2 and then the 1 on the x minus 8.
Yes. You must add up all the exponents. So officially, thank you, Chase, you don't have to go through and FOIL and distribute. That'd be a total nightmare. But if you did do that, you would FOIL here and you would get x squared, blah, 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 something. And then when you multiplied it again, you would multiply it by a x and you'd get x cubed something. And then you'd multiply that by x cubed and you'd get x to the 6th. In order to find your n, or the degree of your polynomial, you're going to, to find n, add the exponents from each factor. Now, I want to make sure it's really clear why we're doing that here, but we did not do that in the previous examples. I'm going to give you a second to write this down, then we're going to go back and look. Look at the big difference here. And it's tricky. So notice that for this example, we were multiplying and multiplying and multiplying. So we had this factor multiplied by that factor. Everything was already factored for us. Contrast that with example 5. The original function that we were given was already split up into terms. So it was much easier to determine the degree of the polynomial because all we had to do was look at the lead term. We didn't have a lead term here because everything was written as factors. Now, once we factored this, you can see that if we wanted to determine n, we could add up 2 plus 1 plus 1, and we'd get to 6. All of your multiplicities, by the way, 3 plus 2 plus 1 add to 6. So that is why n equals 6. So 3 plus 2 plus 1 equals 6. Okay, now 6 is even, as we know. So that changes everything. So for those of you, and I'm sure there were many of you, who were thinking that we had a third degree polynomial with a negative lead coefficient, we actually don't. We have an even degree polynomial. We still would consider our lead coefficient, however, to be negative. This negative in front of the function is not going to go anywhere. It's going to be there no matter what you do. You can't get rid of it. So our lead coefficient is still going to be negative. Or I should say less than 0, just to denote that it's negative. Okay, so n is even. So we know we're either having rises left, rises right, or falls left, falls right. But the fact that the lead coefficient's negative says that we're going to fall left, fall right. So our end behavior looks something like this, and we'll say falls left, falls right. Now, the skeleton for this one would be a little bit more strange, but nothing too crazy. We can jot it down, certainly. I would hate to deprive you of that. So you have zeros at -3, 0, and 8. And there's probably a lot of wacky stuff happening all over this graph, but at least you have some sort of idea of where the interesting stuff is happening by just drawing this skeleton. So you know it falls left, falls right. So it's doing something like this. You know it crosses through. Now, this is where it gets interesting. It crosses at 0 and it crosses at 8, but it touches and turns around at -3. So at -3, the only way for us to touch and turn around would be to approach heading upwards as we move from left to right and then going down. That's the only way for that to happen. And sure, you can connect these because at this point, nothing else interesting is happening between there. Now, we can't really fill in much of what's happening between 0 and -3, but we know that for x equals 0, the graph is going to cross through the x-axis. Now, when you show that the graph crosses, you just need to make sure you denote which way it has to go. If you're following this function, you know it can't cross through anywhere between -3 and 0. So it must do something in between here. We don't know what, so we'll make it dotted. And we'll show it crossing through. And we don't know how steep. We just know it's crossing through. I'm going to guess it goes up pretty high. And then you know that it crosses through at 8. So something is happening in here. We don't know what it is, but we know that it can't cross through the x-axis again. So you would have to then start to plot some points and figure out how high that graph goes to get an idea. You can't guarantee that you know the exact maximum spot there, but you can get close. When you take calculus, you're going to learn how to find the maximum and minimum values on your graph. That'll be super fun. Okay. Questions on 6. I just really love this because I feel like you can see your work a little bit more. Like a lot of times when you're doing work in algebra, it's kind of thankless, you know, you get through it and you're like, okay, done, let's do another one. But you can really start to see how everything pieces together here. What else do we have? All right, I'm going to finish my attendance while you guys do number 7. Oh, no worries, Jan. I think I already had you down from earlier anyway. I was like you guys last week. Our internet was being worked on, and 2 days in a row, it was during my son's class, and he missed all of Friday and like an hour of Thursday, and I felt like I needed to prove to his teacher, like, this is our screenshot. I promise the internet really was out. I'm not lying. If I would have known they were doing work on our internet, I would have run errands or something. But I was in that position where I felt like I had to prove to the teacher that we're not slackers. Okay, finding the zeros for the function. Now, the first one I think is pretty clear. You have x plus 1/5 equals 0, x equals 1/5, and the multiplicity is 4. If the multiplicity is 4, then we're going to touch and turn. The other thing you are probably looking at is that second factor of x squared plus 7 to the 5th power. However, when you take that factor and set it equal to 0, you get x squared equals -7. And then you get x equals plus or minus 7i. We're not going to be talking about imaginary zeros. So we won't need to worry about that. So you're looking for the 0 of, oh, did I say my negative sign must have gotten lost here, unless I just didn't say it at all. Yikes. Negative 1/5 multiplicity 4 touches and turns around B. Oh, sorry, Ben. Yeah, he was asking, why isn't x equal to negative 1/5? I don't know. It is equal to negative 1/5. Sorry. Sometimes I'm talking and writing and thinking about what I'm going to do next, and things get a little scrambled. Any questions on number 7? Okay. A herd of moose. I only find this so funny because I had a student one year who joked about how they should be called meese. And everyone was like, really? Are you sure? And I even was like, really? I didn't know that. He was just like, I don't know. Apparently it's not. Moose plural is just moose. A herd of moose is introduced to a wildlife refuge. The number of moose, n of t after t years, is described by the polynomial function n of t equals negative t cubed plus 24t plus 80. Use the leading coefficient test to determine the graph's end behavior. What does this mean about what will eventually happen to the moose population? First of all, make sure your function's in descending order, which it is. To determine your end behavior, it's n equals 3, so your polynomial has an odd degree. So your graph is going to be doing different things on the left and the right. Because your lead coefficient is negative, be careful not to miss that. Then you have a situation where the graph will eventually seemingly head down from left to right. So the end behavior is rises left, falls right. What does this mean about what will eventually happen to the moose population? Okay, well, think about the fact that t is happening in a number of years, and your function is n of t. So t is acting the way that x would normally act. So if you were looking at something like this, like on some sort of coordinate grid, t would be this axis. N would be your vertical axis. So as t continues to increase, that's what's going to eventually happen. N is, let's see, the number of moose in the population. Yeah, Beth says less moose, which also sounds weird, doesn't it? Yeah, you're right. That means that as t continually gets larger, meaning as time proceeds, n represents the number of moose that you have in a population, and as t gets larger, n is getting smaller. And it doesn't even matter what happens in the middle of this function. All that matters is that eventually t gets larger, n gets smaller. So we can say that eventually the moose population will go to 0. Now, I know that you're thinking, wait, the moose population will eventually decrease to negative values. This is where you have to think about the fact that this is a real life function, even though technically the function models this behavior that takes it underneath the x-axis. We cannot have a population of moose that is less than 0, but we can say that eventually the moose population will decrease to 0, which happens, I guess, to a lot of wildlife these days, as unfortunate as it is. Okay. You know, I'm going to skip this one because I only had one homework question for you to do on it, and I don't really think it's worth spending time on the example to do one homework question. So I'll just take that off your homework. Because we need to talk about graphing. Before we graph, we need to discuss the last characteristic of our graph, which is going to be turning points. Pretty straightforward. In general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. It can never turn as many times as the graph has in its degree. It can be at most n minus 1. Determine the maximum possible number of turning points for the graph in number 11. You should be noticing right off the bat that, whoa, this doesn't look good because we have a higher exponent on the second term. If you can think through that without having to rewrite it, that's fine. I think it's very good to rewrite it. And then we can say that n equals 8. And the highest number of possible turning points you can have is n minus 1, which is 7. If you find that helpful as you go through these graphs, fine. If you don't, fine. You don't have to use that fact, but you might find that it's a useful check. You might find that your graph is doing all kinds of crazy things, and then you're like, wait a second, this is a third degree polynomial. How does it have 4 terms in it? That can't be. Okay. Now, we've sort of been doing this all along. We're going to piece this all together now with example 12. The function is x cubed minus 3x squared. To graph the polynomial function, we're going to basically do all of the things that we have done so far. We're going to determine the end behavior. We're going to find the x-intercepts. When we find them, we're going to determine the multiplicity of each x-intercept and what must be happening to the graph at that point. We're going to find the y-intercept. Sometimes the symmetry will be helpful, but you're going to find that most of the time your functions will not have symmetry. But we know how to compute that because we did that in the previous chapter, 2.2. Use the fact that the maximum number of turning points is n minus 1. That's our procedure. Like I said, we've kind of done this already, but we're really just going to formalize it now and make a full, complete graph. Use the lead coefficient test to determine the graph's end behavior. Notice that your function is already written in descending order. Fabulous. That means that you have n equals 3. If this bothers you, because you're like, wait, didn't we already do this in a different order where we found the intercepts first? That's fine. You can do this in any order you'd like, but since it's written out in this order for the example, I'm going to stick with this order. You have n equals 3. Because you have n equals 3 and your lead coefficient is positive, we know that your graph is going to kind of do that behavior where it goes up from left to right. Something like that. We don't know what happens in the middle. So we're going to say that the end behavior is that it falls left and rises right. If you want to pop that in your graph, fine. I would probably wait until I had some more concrete points because you're going to probably end up erasing it. So I'd probably hold off. Find the x-intercepts. To do that, we're going to factor. So I'm going to take the function, set it equal to 0, and then we're going to factor and solve. So we'll take out the x squared. That leaves you with x minus 3. Now, we have, using the 0 factor property, x squared equals 0 and x minus 3 equals 0. Now, if you don't want to include this particular step of x squared equals 0, that's okay. I would totally understand. I just want you to make sure you know that this 0 has a multiplicity of 2. And x equals 3 has a multiplicity of 1 because your factor only appeared one time. The exponent is 1. Now we're going to state what happens at each 0. So it must be the case that at 0, the graph will touch and turn around at that 0. And at x equals 3, the graph will cross. Oh, how did I miss all this stuff in the chat? Well, I guess it's not that important. Sorry. I'm like, I don't know why. It usually beeps at me. Maybe it's beeping and like I'm not hearing it the same way today. Oh. Interesting. Gian's having audio problems. Is it captioning me, Gian? That's a scary thought. If it is, then it's going to be captioning. Is it captioning me? I don't know. We'll find out later. Okay. All right. So there we've got x equals 0 is a 0 and x equals 3 is a 0. All right. Find the y-intercept. We'll do that next, I guess. F of 0 equals 0 cubed minus 3. Oh, cool. Well, you hope that it's captioning me fine. Times 0 squared is 0. I better make sure I'm extra clear now that I'm being captioned. And if I say something wrong, everything will be kablooey. Okay, there's your y-intercept. Okay, and then graph the function. So go ahead and plop your end behavior on here now, because when we start talking about what the graph is going to look like when it does these things, we need to have sort of an idea of what's happening on the ends. So we know that's going to fall left, and this is the leftmost x-intercept. So whatever is happening has to occur to the left of this point. And I put it pretty close. I mean, I wouldn't put it all the way over here because it's probably going to decrease pretty rapidly. And rise is right. Probably is going to look like that. We can always go through and erase if we have to, unless we're using a pen, which I hope is not the case. Okay, at 0, the graph will touch and turn around. It can only do that if we approach underneath from the left and then head back downward. There's no way in this world that we could touch and turn around above the x-axis. Cannot happen. It has to happen below. So use a little bit of thinking here. Now, don't send this all the way over to x equals 3 because you don't really know what happens in between here. We're going to have to fill in the blanks in a minute. But you do know that it crosses through the graph at 3. So it does something like this. And then it continues to increase forever. Now we're going to go ahead and fill in something there. Now, I don't expect you to be completely exact. Do the best you can. If you would like, once you've done the skeleton, and you should have this work done, you're going to have your calculator as a resource. I have not gotten any word back on my emulator. I'm so sorry, but I'm going to hope that you can kind of see what I'm going to do here. Kind of. You would think that at a time like this, they would be thrilled to give the teachers emulators, but there are all these weird like contract issues. I should just buy my own and just eat the cost of it. Let's see. I don't even know if you can see this. X cubed minus 3x squared. And you can generate some points by looking at the table. So you're going to check your function in your calculator, but I am going to expect to see all of this work. Go to your table, and you can actually find the values there. Do I have this? Oh, sorry, I have a different calculator. Mine is set to ask. Yours is probably set to auto. So I'm going to go back to my table set, which is second table. No, I'm sorry, it's second window. Trying to look at this all sideways. And I'm going to set everything to auto. And I'm going to change my delta table to, I don't know, 1, and I'll just start at 0. I just wanted to generate a list of values for me. Now it's going to graph the function, and I'm at some super weird zoom. Sorry, I found this gold calculator the other day and I missed it, and so I started using it, but I didn't realize all my settings were different. You can do zoom, standard, which is 6. Get a little bit of a closer variation. So you can see it's not going super low because this takes you down to -10. So this only has to be, I don't know, not even halfway down. But go to your table and you can start to look at what some of these values are. Hopefully you guys have your calculators on you. If you don't, you can always compute these values. But my table, sorry, this is just nuts that I'm trying to show you this like this. I can lower the color a little bit. Doesn't help much. Okay. I know that when x equals 1, y is -2. So from my table, I have the point 1, -2. I also have the point 2, -4. That's good. Plot those points on your graph. 1, -2, 2, -4. And I know what some of you are thinking. If we were just going to use our graphing calculators, then what's the point? Technically, you shouldn't use them all the time. You're supposed to be able to find this information without your graphing calculator. Technically, I didn't need my graphing calculator to find those points. But I think it's important that we know how to check our work, which we'll do on the graphing calculator. And if you have some crazy function that's hard to evaluate, you might want to go to your table to find those points. But all the graphing calculator did was it found f of 1 and f of 2. That's where those points came from. So f of 1 was just 1 minus 3, which was -2. And f of 2 is 2 cubed, which is 8, minus 3 times 4, which is -4. And that's where those numbers came from. Now, again, we're making a big assumption here that the lowest point on the graph is at 2, -4. When you're in calc, you'll be able to find that exact minimum value. In this class, I can't expect you to give me any guarantees, but I want you to get close. So it could be that maybe the lowest value is at, I don't know, 1.5. Maybe it goes a little bit lower here and we just can't see it. I can't expect you to get that precise in college algebra. Get as close as you can. Okay, and this is what you're going to be doing for the graphing by hand homework. Just filling in that skeleton of the graph, or just putting the skeleton down and then filling it in just by evaluating the function at a couple different points. I would actually say try not to use your calculator until you get to the end and you're doing your check. Questions on the graph? Okay. Wonderful. Well, I still have 10 minutes, so I'm going to plant the seeds for long division of polynomials. Okay. Now, you may or may not have done this before. My guess is most of you have, but you don't remember it very well. Sometimes when we say long division, people get upset. They don't like long division. And you use long division together with polynomials and it sounds terrible. Students tend to do really well with this. We're going to talk today about long division, and then next time we're going to talk about synthetic division, and then we'll talk about how all of this applies to finding the zeros of a function, where you can't factor. So that's kind of what this is leading to, just working towards being able to find the zeros of a function, which we'll be spending a lot of time in on 3.4, and then using those zeros to solve an equation. So to long divide your polynomials, you are going to make sure to arrange the terms of both the dividend and divisor in descending powers for any variable. And if you're not sure what these things are, like what's the dividend, what's the divisor? The dividend goes underneath the long division symbol. The divisor is what you're dividing by. And then you have a quotient, that's your answer. And sometimes you'll have a remainder. We're going to be very systematic about this. We're going to complete a round once, and then we're going to go down to the next line, and we're going to do the same thing over again until we get to the bottom. And if you're not sure when you're done, I'll make sure that we talk about how to know when you're done. We're going to divide the first term in the dividend by the first term in the divisor. The result is the first term of the quotient. Then we're going to multiply through. You know, I think doing this is better than reading the directions. The directions are kind of, I guess, helpful if you're in the moment of working on them and you're not sure what to do next. I actually don't ever read these directions. I just say, watch me do this and you'll get the hang of it. But you have the directions there as a reference. Okay. We're going to write this in the form of long division. We're going to make sure that our dividend and divisor are both in descending order. We're also going to make sure that we're not missing any factors of x in the dividend. If we were to be missing something, like let's say we had 9x squared minus 7, and this minus 62x wasn't there, we would need to fill it in with a placeholder. So we're going to do that too. But for right now, we just have a very straightforward long division problem. Every factor of x is accounted for. We have a constant. And then we have in our divisor x minus 7. So this guy is your dividend, and you're dividing it by x minus 7. Okay, so you're going to start out by taking the first term in your dividend. Take it off to the side, wherever you'd like for it to go. And you're going to divide it by the first term in your divisor, which is x. When you divide this out, you just get 9x. That is the first term in your quotient. I like to line these up so that the x's are with the x's. It's up to you. It's not the end of the world if you don't. Okay, so the first thing you're doing is dividing the first term in the dividend by the first term in the divisor. The quotient goes in your quotient. The next step is to multiply. You're going to multiply this term in your quotient by both of the terms in your divisor. So you're going to take 9x and you're going to multiply it by x minus 7. And that quantity is going to go on the next row. You're going to put it right here. So 9x times x is 9x squared. If you've done this correctly, you will get the exact same quantity in the dividend that you originally had. 9x times negative 7, account for that negative sign, is negative 63x. Now, whenever you're using long division, you are subtracting, not adding. This whole quantity in the second row is going to get subtracted from the first row. Some students like to just change each sign instead of using parentheses. They'll just go, okay, minus, plus. If you want to do that, do that. I don't like to do that because I think it just looks confusing in my notes later. All right, so 9x squared minus 9x squared is 0x squared. You don't need to include it. That will always happen if you've done this correctly. Negative 62x minus negative 63x is negative 62x plus 63x, which is just x. Once you've done the subtraction, pull down anything that's remaining. You want to just show everything that's left from the original dividend. So pull down that -7. And then you're going to repeat the process over again. So now, instead of treating your old dividend as the dividend, you're going to only be looking at this row. Do the same thing. So you're going to take the first term of your dividend, which we'll now call x minus 7. So that's x, and you're going to divide it by the first term in your divisor. And you'll get 1. Now that's good. X divided by x is 1. That's the quantity that goes into the quotient. It's positive 1, so put a plus sign in front of it. Had it been negative 1, you would have put a minus sign in front of it. Now, the last time we did this, we took 9x and we multiplied it by x minus 7. This time we're going to take 1 and we're going to multiply it by x minus 7. So 1 times x is x. 1 times negative 7 is negative 7. And you are always subtracting the quantity. X minus x is 0. Negative 7 minus negative 7, don't forget the double negative, is negative 7 plus 7, which is 0. You're done. In this case, you have no remainder because you don't have a quantity that's left over that's not 0. If your remainder is 0, you don't write it. It's done. So your quotient is 9x plus 1. Now you can always check this by multiplying your quotient times your divisor. So you're going to take your quotient times your divisor plus any remainder you have. In this case, you don't have one. And that will equal your dividend. And that's it. I don't have time to do another one. So for your homework, I'm just going to put up like 1 or 2 basic ones like this where you don't have a remainder to worry about that you can work on. There might only be 1. I don't know. We'll see. And then we'll continue with long division next time. I think I'm going to replace the problem in number 2 because the numbers are kind of crazy. And my whole goal is not to just give you crazy, crazy numbers. It's to get you to long divide. Okay, so that is all. For your homework by hand from 3.2, I am going to send out an email. I'm going to put a Dropbox folder on there, scan it into a PDF. 1 file. So just keep scanning until you're done, and it will combine all your pages into 1 PDF file. It will be numbers 44, 46, 47, 56, 59, 63, and those will either be in the physical text you got from the bookstore or the e-text that you can find for our book on my math lab. It'll be under chapter contents or under e-text on page 378 in section 3.2. I will send out an email though to remind you of the directions. Graph paper would probably be helpful, but it's not the end of the world if you don't have it. But I'll set up a Dropbox folder for you on D2L so you can submit that. It will be due a week from today. I also put up some of my math lab homework for you from 3.2 for talking about end behavior, multiplicity, and finding zeros. All the graphing you're going to do by hand. But yeah, there's some of my math lab stuff on there that I thought would be really helpful, just the pieces of that we discussed before we got to the graphing. And that's it. I'm going to be online for the next 15 minutes. If you have questions, stick around. Otherwise, I will see you on Wednesday. Have a wonderful evening. Bye-bye. Bye.